Hi everyone, welcome to the Remote Transport Operations Lab. We are Group 7. Our project is about how we could measure the density of a fluidized bed and how the height of the glass beads changes when the bed is fluidized.
Fluidization was discovered in the 1920s by a German chemist, Fritz Winkler. Fluidization consists of a solid packed bed being brought into a fluid-like condition. The media, which in our project was glass beads, undergo the influence of pressurized air, which is the fluid in this case, and that results in the media acting like a fluid. On the image, you guys can see the little black dots represent the holes that were drilled into the little tubes, pipes that we use for the project. And those allowed the air to flow into the fluidized bed. The objective of this experiment was to determine the bed's height dependence on the pressure and to determine the overall density of the bed using several objects that were of known density. At first, we hypothesized that there was going to be a linear correlation between the pressure and the height of the bed, and that we were going to be able to determine the density of the bed by using interpolation of the highest density objects that were introduced in the fluidized bed and the low density objects that floated. Now we're going to introduce the safety aspects of our project.
Let's see what happens.
So theoretical background for this experiment was relatively simple and straightforward. We started with the Karman-Kozeny equation that you can see on the left side of your screen. We used this equation to find and estimate minimum fluidization velocity that must be achieved to start the fluidization process. We then used that value to estimate the superficial velocity, which would be at least 10 times larger than minimum fluidization velocity. When we estimated the superficial velocity, we then determined the pressure difference, and we found out that the air compressor that we were about to use must be sufficient enough for the successful experiment. We then, to determine the height difference of the fluidized bed, we used the equation on the right side of the screen together with the diagram under it. Basically, the point of this equation is the void coefficient epsilon changes once you start the fluidization process. It grows larger, and we use this information to determine the height difference of the bed. We predicted it to be around 3 millimeters, which was extremely close to the experimental value we obtained later. Then initially, our plan to determine the density of the fluidized bed was to interpolate the values of the densities of two objects. One of them would sink and one of them would float on top of the bed. And that how we wanted to calculate the overall density of the fluidized bed. But then we noticed once we started the experiment that the spherical objects, a lot of them, they did not submerge completely and they did not float on the surface of the bed. So we used the relations between the densities of the object and the volume submerged to determine the overall density of the fluid, which in our case would be the fluidized bed.
So as you see here in the table on the left, we have all the densities of all the objects we tested on. And as Yair mentioned, the pink rubber ball was the one that was partially submerged when the bed was fluidized. So we used a calculated density, multiplied it by the volume, like how much what fraction of the volume that was sunk. As you see in the video on the bottom left, in slow motion, you could see the exact moment that the bed is fluidized, and some of the objects start sinking because they are more dense than the bed, whereas some objects start floating and bouncing. We also measured the density at various pressures, and as you see in the graph, as pressure increases, the density of the fluidized bed decreases. Here we also measured how much the height changes as a function of pressure. So in the video on the right in slow motion, you can see that the bed rises about 3 millimeters. So if you just keep going back and forth, you can see it rising. So we did this for varying pressures, and we saw that as pressure increases, the height of the bed also increases.
After fluidization, we have noticed that these couple elements that are floating and other sink. The focus will be on the floating element, which we will use to determine the value of the density of the bed. Among the floating elements, we will focus on the bouncy rubber ball and the ping pong ball, which have respectively the highest and the lowest density. Using the Archimedes principle, we have gotten to the conclusion where the density of the bed is estimated to be similar to the density of the bouncy rubber ball. At the pressure 25 psi, we have noticed that the height obtained was 0.15, and we decided to increase the pressure. As we increase the pressure, we have noticed a significant change in the height. So we got to the conclusion where the increase of pressure is the increase of pressure and the increase of pressure increase the height as well. And we also have noticed that as we increase the pressure, the density of the bed decreases. So the increase of height can be explained by the slug formation, which lead to a regular distribution of pressure drops in the bed. And among the solution that we have found to have a better process, we decided to use smaller size bits using a process at high pressure drop and a higher pressure drop, sorry. And at the end of our experiment, we get to the conclusion where our process was satisfying because we noticed that the height changed as a function of pressure and the density changed as a function of pressure as well. And the main conclusion of the experiment was that to conclude that the density of the fluidized bed that we calculated was similar to the one that we found experimentally. Next.
Some things we could have done differently. We could have used a cylindrical tube or drill holes into the corners so airflow reaches the corners. Use a bigger tube so the tubes reach the whole perimeter and there's even airflow throughout the bed. Use a smaller drill bit to avoid glass beads going into the tubes. Or install a flow meter for more precise velocity calculations and a better pressure gauge for more accurate calculations.
Thank you for listening to our presentation.